Welcome to this walkthrough of LeetCode problem number 1905, Count Sub-Islands. In this problem, we'll explore how to determine the number of islands in one grid that are completely contained within another grid. It's a fascinating problem that combines concepts of graph traversal and island detection. Let's dive in. In this problem, we are working with two binary grids, grid 1 and grid 2, where each grid is represented as an m by n matrix. The cells in these grids can either be 0, representing water, or 1, representing land. An island is defined as a group of land cells, or ones, that are connected either horizontally or vertically. Any cells outside the grid are considered water. The goal is to determine the number of sub-islands in grid 2. A sub-island is a group of connected land cells in grid 2 where every cell in that group is also part of an island in grid 1. The output of this problem will be an integer representing the total number of sub-islands in grid 2. This means we are essentially comparing islands in grid 2 with those in grid 1 to determine how many are fully contained within the islands of grid 1. Now, let's look at the first example. Here, grid 1 and grid 2 are both 4 by 5 matrices. In grid 1, we see a large island in the top left corner that spans multiple rows and columns. In grid 2, there is a similar structure, but one of the land cells in the bottom left corner does not overlap with the island in grid 1. The output for this example is 1, as there is only one sub-island in grid 2. This sub-island is the top left part of grid 2 that completely overlaps with the corresponding island in grid 1. The mismatched bottom left cell in grid 2 prevents the entire island from being considered a sub-island. To further clarify, in the first example, the top left island in grid 2 qualifies as a sub-island because every cell in this group of ones corresponds to a land cell in grid 1. However, the bottom left cell in grid 2 does not align with land in grid 1, so it is excluded from being part of a sub-island. Moving to the second example, we have two grids where grid 1 contains several distinct islands, and grid 2 also has multiple islands. The output in this case is 2. The reasoning is that there are two valid sub-islands in grid 2. The first is the top left island, which entirely overlaps with an island in grid 1. The second is the bottom right island, which also perfectly overlaps with a corresponding island in grid 1. However, the small island at position 2, 3 in grid 2 is not a sub-island because it does not fully align with any island in grid 1. In this second example, it's important to note the distinction between valid sub-islands and islands that partially overlap. The top left and bottom right islands in grid 2 are valid sub-islands because every single cell in these islands corresponds to a land cell in grid 1. The small island at position 2, 3 in grid 2 fails this condition, as it contains cells that are not part of any island in grid 1. Now, for the third example, we have smaller grids where both grid 1 and grid 2 are 3 by 3 matrices. In grid 1, there is one large island that spans almost the entire grid, while in grid 2, there is a similar structure with one large island. The output here is 1, as there is only one sub-island in grid 2 that is completely contained within the island in grid 1. In the third example, the single island in grid 2 qualifies as a sub-island because all of its land cells align perfectly with the corresponding land cells in grid 1. There are no mismatched cells or partial overlaps. This makes it a straightforward case where the output is simply 1. Now, let's consider the constraints of the problem. The grids are guaranteed to have the same dimensions, with m rows and n columns. Both m and n can be as large as 500, so we need to think about the efficiency of our solution. Additionally, the values in the grids are binary, meaning each cell is either 0 or 1. These constraints ensure that we can focus on developing an efficient algorithm to handle large grid sizes without worrying about unexpected input formats. Finally, let's discuss some edge cases. If grid 2 has no islands, meaning it contains only water cells, the output should be 0 since there are no sub-islands to count. Similarly, if all islands in grid 2 perfectly overlap with grid 1, the output should be the total number of islands in grid 2. On the other hand, if grid 1 is completely water, meaning all cells are 0, then the output will also be 0 because no islands in grid 2 can be sub-islands. Lastly, if grid 2 is entirely water, the output will again be 0, as there are no islands to evaluate. These edge cases help ensure our solution handles scenarios where the grids are either entirely water or perfectly aligned. To solve LeetCode number 1905, The task is to count how many islands in Grid 2 are entirely contained within islands in Grid 1. Here, an island is defined as a group of connected ones, where connections are limited to the 4 cardinal directions. One potential solution is the brute force approach. The intuition behind this method is to individually check each island in Grid 2 to see if all its cells overlap with an island in Grid 1. To implement this, we would first traverse Grid 2 to locate all islands. Then, for each of these islands, we would verify cell by cell whether each part of the island lies within an island in Grid 1. If all the cells meet the condition, the island is counted as a sub-island. However, this approach is computationally expensive. The worst-case time complexity is O, open parenthesis m times n close parenthesis squared, where m and n are the dimensions of the grid, because verifying each cell for every island involves repeated and redundant checks. This makes the brute force approach impractical for larger grids. A more efficient solution leverages depth-first search, DFS, with overlap validation. Instead of performing redundant checks for every cell, this approach combines island traversal and validation into a single process. The key insight here is that if any part of an island in Grid 2 extends outside an island in Grid 1, meaning a cell in Grid 2 has a value of 1 while the corresponding cell in Grid 1 is 0, the entire island is disqualified as a sub-island. Using DFS, we can efficiently traverse connected components in Grid 2 while simultaneously validating overlap with Grid 1. The process begins by traversing Grid 2. For each unvisited cell with a value of 1, a DFS is initiated to explore the island. As the DFS progresses, it checks that all ones in Grid 2 overlap with ones in Grid 1. If a mismatch is found, the island is invalidated. If no mismatches occur, the island is counted as a sub-island. Additionally, visited cells are marked to prevent redundant checks. This approach ensures that each cell is visited only once, resulting in a time complexity of O, m*n, making it significantly more efficient than the brute force method. The DFS approach is chosen because it strikes a balance between simplicity and efficiency. By integrating island identification and validation into a single traversal, it eliminates unnecessary computation and performs well even on large grids. An alternative strategy is to use breadth-first search, BFS, with overlap validation. Like DFS, BFS traverses islands and checks for overlap with Grid 1. However, instead of recursion, BFS uses an explicit queue to explore connected components. The steps involve traversing Grid 2, initiating BFS from each unvisited cell with a value of 1, validating overlap during traversal, and marking visited cells. The time complexity is also O, m*n, comparable to DFS. Despite being a viable alternative, BFS is not chosen because it introduces additional complexity due to queue management. DFS, on the other hand, is simpler to implement recursively and avoids the need for explicit data structures, making it a more intuitive choice for this problem. The chosen strategy is DFS with overlap validation because it offers a combination of simplicity and optimal performance. The single traversal ensures efficiency, and the recursive implementation is straightforward, avoiding the need for managing data structures like queues. However, there are trade-offs to consider. Since DFS uses recursion, it may encounter stack overflow issues for extremely large grids. This can be addressed by using an iterative DFS approach or applying tail recursion optimization in some programming languages. While BFS is a comparable alternative, it introduces additional overhead due to queue management without offering a clear advantage. Ultimately, DFS with overlap validation is the most efficient and intuitive approach for solving this problem within the given constraints, making it the ideal choice for implementation. To solve the problem of counting sub-islands, we employ a depth-first search, or DFS, approach. Let's break this down step by step. First, we need to understand the problem clearly. An island is defined as a group of ones in the grid that are connected in any of the 4 cardinal directions, up, down, left, or right. Our goal is to determine how many islands in Grid 2 are completely contained within the islands of Grid 1. This means that every cell in an island of Grid 2 must directly overlap with a corresponding one in Grid 1. Next, the input data consists of 2 binary grids of the same dimensions, where 1 represents land and 0 represents water. The algorithm involves iterating through the cells of Grid 2. Whenever we encounter an unvisited one, we consider it the start of a new island. Through DFS, We traverse the entire island in grid 2 and validate whether all its cells overlap with corresponding land cells in grid 1. If they do, we count it as a sub-island. Finally, we sum up all such sub-islands to get the result. The next step is to detail how the algorithm works. First, we need to define a DFS function. This function will explore connected ones in grid 2, marking them as visited by setting their value to 0. At the same time, it will check whether each one in grid 2 corresponds to a 1 in grid 1. If any mismatch is found, the island is deemed invalid. Then, we initialize a counter to track the number of valid sub-islands, starting at 0. We also choose between using a visited set or modifying grid 2 directly to prevent revisiting cells. Now, for each cell in grid 2, if it contains a 1, we call the DFS function to explore the island starting at that cell. If the DFS traversal confirms that the island is valid, we increment our counter. The DFS traversal itself has a base case to handle out-of-bound indices, water cells, or already visited cells. During traversal, it recursively explores all 4 neighboring cells and determines if the entire island is valid. After processing all cells in grid 2, we simply return the counter as our result. There are a few key insights that make this algorithm effective. First, DFS is ideal for this problem since it systematically explores connected components in the grid, ensuring we visit every cell in an island exactly once. Second, the validation of sub-islands is built directly into the DFS traversal, allowing us to check whether all ones in grid 2 align with ones in grid 1 as we traverse. This saves us from needing a separate validation step. Additionally, to optimize memory usage, we modify grid 2 in place by setting visited cells to 0 instead of maintaining a separate visited set. This approach is efficient and avoids unnecessary overhead. Now, let's consider some edge cases. If grid 2 contains no islands at all, the result will naturally be 0. Islands in grid 2 that only partially overlap with islands in grid 1 should not be counted, as all cells in the grid 2 island must align to qualify. Finally, the algorithm handles grid boundaries carefully by checking indices before accessing cells, avoiding any out-of-bound errors. Now let's analyze the complexity of the algorithm. The time complexity is O(m*n), where m and n are the dimensions of the grids. This is because every cell in the grid is visited at most once during the DFS traversal. The space complexity is also O(m*n), in the worst case, which occurs when the largest island spans the entire grid, leading to a deep recursive call stack. To solidify our understanding, let's look at an example. Suppose we have grid 1 and grid 2 as follows. Grid 1 contains 3 distinct islands, while grid 2 contains 2 islands and a solitary one in the center. Our task is to figure out how many of these islands in grid 2 are sub-islands. Using the algorithm, we begin by iterating through grid 2, and for every one we encounter, we initiate a DFS to validate the island. The output for this example is a sub-island count of 2. Here's why: the first island in the top left of grid 2 perfectly overlaps with the corresponding island in grid 1. Similarly, the second island in the bottom right of grid 2 also completely overlaps with its counterpart in grid 1. However, the single one in the middle of grid 2 does not form a valid sub-island, as it does not align with a corresponding one in grid 1. This example clearly illustrates the importance of ensuring that every cell in the grid 2 island matches with grid 1. By following this approach, we identify all valid sub-islands and return an accurate count. This is a Python solution for LeetCode problem number 1905, Count Sub-Islands. The objective is to count the number of sub-islands in grid 2 that are entirely contained within the islands of grid 1. Here's the explanation of the code. 1. DFS approach. The main idea is to use depth-first search, DFS, to traverse each island in grid 2. For each cell, we check if it is part of a sub-island that is entirely within grid 1. 2. DFS helper function, DFS. This function recursively marks the visited cells in grid 2 by setting them to 0. While traversing, it checks if the current cell in grid 2 corresponds to land, 1, in grid 1. If a cell in grid 2 is water or out of bounds, the function returns true. The is_sub_island variable keeps track of whether the current island in grid 2 is a sub-island. The function recursively explores all 4 directions, up, down, left, right. 3. Iterate over grid 2. The main loop iterates over each cell in grid 2. If a cell contains land, 1, we call the DFS function to check if the island starting from that cell is a subisland. If DFS returns true, we increment the counter. For edge case handling, the algorithm handles edge cases, such as when grid 2 has no islands or when all islands in grid 2 are not subislands of grid 1. It ensures that visited cells are not revisited by marking them as 0. 5. Time complexity. The solution runs in O, m*n, where m and n are the dimensions of the grids. Each cell is processed at most once. 6. Space complexity. The space complexity is O, m*n, in the worst case due to recursion depth in DFS. This implementation is efficient and concise, making it well suited for the constraints of this problem. Here, we begin the implementation of the count subislands method. The method takes two 2D integer arrays, grid 1 and grid 2, as inputs. Grid 1 represents the original islands, and grid 2 represents the islands we want to evaluate as subislands. First, we determine the number of rows and columns in grid 2, and initialize a variable subisland count to 0, which will keep track of the number of subislands. Next, we use nested for loops to iterate through each cell in grid 2. If a cell contains land, represented by the value 1, we call the DFS method to perform a depth-first search. If DFS returns true, it means the current island in grid 2 is a subisland of grid 1, so we increment the subisland count. Finally, we return the total count of subislands. The DFS method begins by verifying whether the current cell is within bounds or if it's water in grid 2. If it's out of bounds or water, we return true since this part doesn't disqualify the island as a subisland. We also mark the cell as visited by setting it to 0 in grid 2 to avoid revisiting it during the search. Now, the DFS method continues by checking if the corresponding cell in grid 1 is land. This determines whether the current cell can be part of a subisland. We store this result in the variable isSubisland. Then, we define two arrays, dx and dy, which represent the four possible directions of movement: right, down, left, and up. Using a for loop, we recursively call the DFS method for each neighboring cell. The result of each recursive call is combined with the current isSubisland value using a logical AND operation. This ensures that if any part of the connected island in grid 2 does not overlap with land in grid 1, the entire island is disqualified as a subisland. Finally, after exploring all directions, we return the isSubisland value, which indicates whether the entire connected component in grid 2 qualifies as a subisland of grid 1. In this problem, we are tasked with counting subislands in grid 2 that are entirely contained within islands in grid 1. An island is simply a group of connected 1s in the grid. A subisland in grid 2 means that every one in that island must overlap with a corresponding one in grid 1. To solve this, we use depth-first search, or DFS, to systematically explore each island in grid 2 and determine if it meets the subisland criteria by comparing with grid 1. For example, in the given grids, we can see that grid 1 and grid 2 both contain islands, and our goal is to count how many of those in grid 2 are subislands of grid 1. By marking cells as visited and comparing them step by step, we can determine their validity one island at a time. To begin, we initialize a variable count to 0, which will keep track of the number of valid subislands. Then, we iterate through each cell in grid 2 to identify potential islands. When we encounter unvisited 1s, we initiate a DFS from that cell. For the first island, starting at position 0, 0, we mark the cell as visited by setting grid 2, 0, 0, to 0 and explore all its neighbors in four possible directions. As we traverse the island, we continuously verify each cell against grid 1 to ensure all corresponding cells in grid 1 are also 1. Since this island satisfies the subisland condition, we return true and increment count to 1. Similarly, for the second island starting at 2, 0, we follow the same process, marking cells as visited, validating against grid 1, and confirming it as a subisland. After incrementing count again, the final result for this example is count equals 2. Now, let's take a look at another example with different grids. Here, grid 1 and grid 2 have islands of varying shapes and overlaps. Once again, we initialize count to 0 and begin exploring grid 2. As we perform DFS on the first island starting at 0, 0, we encounter a cell in grid 2, specifically 1, 1, that does not have a corresponding one in grid 1. This invalidates the island as a subisland, so we return false and do not increment count. Moving on to the second island, which begins at 2, 2, we validate that all its cells in grid 2 have matching 1s in grid 1. Since this island meets the criteria, we return true and increment count to 1. The final result for this example is count equals 1. For the third example, the grids are smaller, but the process remains the same. We start with count equals 0 and identify two islands in grid 2. The first island begins at 0, 0. Performing DFS, we confirm that all its cells in grid 2 correspond to 1s in grid 1. This island is valid, so we increment count to 1. The second island starts at 0, 2, and again, every cell matches perfectly with grid 1. After marking this as a valid sub-island, we increment count to 2. At the end of this example, the total number of sub-islands is count equals 2. To summarize, the key to solving this problem is systematically exploring each island in grid 2 using DFS while checking its validity against grid 1. By marking cells as visited, validating overlaps, and incrementing the count of sub-islands only when all conditions are satisfied, we can efficiently determine the result. Across the examples, we've seen how to handle cases where islands overlap partially, fully, or not at all. This approach ensures that we accurately count the sub-islands in grid 2 while adhering to the constraints of the problem. The time complexity of this solution is m*n, where m represents the number of rows and n represents the number of columns in the grids. To understand this, let's break it down step by step. First, during the outer loop traversal, the algorithm iterates over every cell in grid 2 using two nested loops. This results in m*n iterations. Next, for any cell in grid 2 that belongs to an island, which is identified when grid 2, I, j, equals 1, a depth-first search, or DFS, is initiated. In the worst-case scenario, the DFS might explore every cell of the island. However, since each cell is marked as visited by setting it to 0 after being processed, no cell is revisited. This ensures that the total number of DFS calls and steps stays bounded by the total number of cells, m*n. Combining these steps, each cell is either processed during the traversal or the DFS, but not both, making the overall time complexity proportional to m*n. Now, let's analyze the space complexity, which in the worst case is m*n. This is primarily due to the recursion stack used by the depth-first search. The maximum depth of the recursion stack is determined by the size of the largest island in grid 2. If the entire grid forms a single island, the recursion stack could grow as large as m*n. Additionally, the input grids grid 1 and grid 2 require m*n space, but since these are part of the input, they are not counted as additional space. Importantly, no extra data structures are used beyond the recursion stack, meaning there is no additional auxiliary space. Therefore, the space complexity of the algorithm is m*n in the worst case. Let's compare this optimized depth-first search approach to a brute force method. A brute force strategy might involve individually checking every cell in grid 2 against grid 1, leading to redundant computations as overlapping islands could be processed multiple times. This inefficiency could result in a time complexity far worse than m*n. In contrast, the DFS method avoids redundant processing by marking visited cells, ensuring each cell is handled only once, which makes the algorithm linear in the number of cells. Now, considering different scenarios, in the best case where grid 2 contains only water, meaning all cells are zeros, the DFS is never invoked. Here, the complexity simplifies to just the traversal of grid 2, resulting in m*n, time and 1 space, excluding the recursion stack. For average cases, where there's a mix of land and water, the DFS processes each island exactly once, and the complexity remains m*n for both time and space. In the worst case, if grid 2 consists of a single massive island, the DFS would recurse through all m*n cells. This would result in a time complexity of m*n, as each cell is visited exactly once, and a space complexity of m*n, due to the recursion stack depth. To confirm this, we can reason mathematically. Every cell is either visited during the initial traversal or during the DFS, but not both. Additionally, the depth of the DFS stack is limited to the size of the largest connected island, which is at most m*n. This ensures that the algorithm's time complexity is O, m*n, and its space complexity is also O, m*n in the worst case, making it efficient for this type of grid-based problem. One of the most common mistakes in solving the count sub-islands problem is confusing the traversal order of the grid. Without a systematic process, such as skipping cells prematurely or revisiting already processed cells, you risk missing islands entirely. To avoid this, either maintain a separate visited array or mark cells directly in the grid as visited during traversal. Another error occurs when mismatched grid sizes are not accounted for. If you assume grid 1 and grid 2 are the same size, you might inadvertently access out-of-bound indices, leading to runtime errors. Always validate the dimensions of the grids and ensure traversal is within the bounds of both. Lastly, it's crucial to properly distinguish sub-islands. If you count an island in grid 2 as a sub-island without verifying that it's fully contained within grid 1, you'll violate the problem's constraints. During DFS, confirm that every land cell in grid 2 is also part of grid 1 to ensure correctness. Inefficient implementations of DFS or union find can also lead to challenges in this problem. Repeatedly traversing the same cells or failing to control recursion depth can significantly increase the time complexity of your solution. To address this, consider optimizing with memoization or using an iterative DFS approach to reduce redundant computations. Another frequent issue is improper marking of visited nodes. If you forget to mark cells as visited in grid 2, you might encounter infinite loops or unnecessary rechecks, which could lead to incorrect results or even a stack overflow in a recursive DFS. A reliable solution is to mark cells as visited by setting them to 0 or using another placeholder value that ensures they won't be processed again. This problem is an excellent opportunity to demonstrate your understanding of grid traversal algorithms like DFS and BFS, along with how to manage visited states effectively. A critical aspect is verifying containment between grids, which often requires layering multiple conditions. There's also room to discuss optimization. While DFS is often simpler to implement and debug, Union Find offers better scalability on larger grids. You should be ready to explain the trade-offs between these approaches. Be mindful of edge cases, such as handling empty grids, fully overlapping grids where grid 2 is identical to grid 1, and non-overlapping grids where no sub-islands exist. During an interview, clearly articulate your thought process. For instance, explain how you ensure correctness by marking cells as visited and verifying full containment of islands. This problem is closely related to several other LeetCode questions that test grid-based traversal techniques. For example, LeetCode number 695, Max Area of Island, focuses on finding the largest connected island in a grid, which is a foundational concept for this problem. LeetCode number 1254, Number of Closed Islands, challenges you to identify islands fully surrounded by water, requiring careful edge case handling. Another related problem is LeetCode number 1020, Number of Enclaves, where you count land cells that are unreachable from the grid's border. Finally, LeetCode number 200, Number of Islands, is a classic problem that lays the groundwork for grid traversal using DFS or BFS. Practicing these problems will deepen your understanding and prepare you for variations like count sub-islands. There are several alternative approaches to solving the count sub-islands problem. The union find method, also known as disjoint set union, treats grid cells as nodes in a graph and groups connected components using union and find operations. This approach is efficient for large grids with an amortized time complexity of O, n*log n, but it requires a more complex implementation. Another option is the flood fill technique, which uses DFS or BFS to traverse islands in grid 2 while simultaneously verifying containment in grid 1. This method is simpler to implement but may be slower on larger grids. Lastly, a two-pass approach can be used. In the first pass, you identify all islands in grid 2, and in the second pass, you verify their containment in grid 1. This separation of logic makes the implementation clear but may require additional memory to store island data. Great job following through with this problem. We've covered the key concepts behind solving count sub-islands using graph traversal techniques like DFS and BFS. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!